Welcome everyone to our first lesson in Unit 5. Today's lesson is going to be on atomic theory and the history of atomic structure and how we came to our current understanding of the atom and the model that we currently use to describe its shape and structure. So by the end of today's lesson, you should be able to use the experimental evidence presented to you in the lesson to describe the model of the atom. And models, if you think of like a model airplane or a map of the world, it is a representation of something that is real. And since we don't directly see atoms, we have to kind of use a model to describe its structure because we can't actually see it. And we get this information from several different experiments throughout history that have led us to our current understanding of what the atom may or may not look like. So we're going to take a little trip here through time. We're going to start in the past and move towards the more recent past, can be considered the present, and take a look at how the model of the atom changed throughout time. And this mainly changed along with technology. So as technology changed, our understanding of science increased, and vice versa. They kind of drive each other. Now throughout this lesson, you guys have a spot in your notes to take some important pieces of information on each of these 6 different atomic models. And you're going to want to record the time frame around when each of these models was developed and a couple of the key points for each of these models on each of these slides. Now, in the beginning, our humble beginning here was Democritus, several thousand years ago, 460 to 370 BC. And he basically said that there are basic elements from which everything that we know about, all matter, is going to be made from, basic building blocks. And that everything is going to be composed of small atoms moving in this void. And this was a thought experiment. And he figured that if you take something and cut it in half so many times over and over and over again, you can eventually get to a point where we can't cut it down any further. It's going to be indivisible, which in Greek is atomos, and that's how we got atoms. And he figured that some atoms could be round or pointy or oily or have hooks to account for their different properties. So that was going to be a specific part of the atom itself that gave it those particular properties. And Democritus' model was just a simple indivisible sphere, like a marble. So it's a very basic structure. And we'll see kind of throughout each of these models how the location and understanding of specific subatomic particles changes. Now we go over 1,000 years, over 1,500 years to get to John Dalton with the next development of the model. Again, we're going to have a big change in technology over those 1,500 years, which allows us to do different experiments, come up with different data to help us understand more about our world, and in this case, about atoms. So John Dalton first introduced his ideas in 1803, and he said that atoms are the smallest part that any sample of an element can be broken into. So these atoms are going to make up elements, and that's the smallest indivisible part of the atom. Now we figured that all atoms of a given element are going to be identical. They're going to have the same atomic mass. Different elements would have different atomic masses, but elements or atoms of the same element would be identical, and they would differ from those of any other element. He also came up with this idea that atoms can either be created or destroyed in any chemical reaction. So they're just going to be kind of used and reused. We're never going to come up with new ones or get rid of other ones, thinking of our law of conservation of mass. And he figured that a given compound is always going to have the same relative numbers and kinds of atoms. For example, water is always going to be found in a 2-to-1 ratio of hydrogen to oxygen. And he did this with an experiment using a battery where he connected a current to a sample of water and was able to split the water up into hydrogen gas and oxygen gas. And he developed this law called the law of definite proportions, which said basically that atoms of the same elements are going to have the same atomic mass, and that the ratio of the masses is always going to be the same when combined in a compound. And he found that for water, when he separated this using electricity, he always found that the mass of oxygen was 8 times the mass of that of hydrogen. So that's how he came across, or in one way, started to come up with some data to kind of prove that water had a formula of H2O. Now Dalton's model was pretty similar to that of Democritus. These small indivisible spheres where we can have different kinds and they can be put together in certain ratios to form compounds. So they can exist by themselves, they can exist combined with each other in definite proportions. Now J.J. Thomson comes around. This is going to be much more closer to John Dalton, so not as much time's passing here in between. And he came up with this model using data that he got from this cathode ray experiment, which was using what we call a Crookes tube. And these ultimately came to use in our old school large televisions and old monitors, not really the flat ones that we use now, that's a different technology, but the ones that kind of have a depth to them. The old school TVs that are really big and heavy have this cathode ray tube in them. That's why they're called CRT televisions or CRT monitors. And his model was called the plum pudding model. He came out with this in the early 1900s. And basically that model said that we have electrons in a soup of positive charges. And, well, plum pudding, really, no one really eats plum pudding anymore, so a better way to name this model would be a chocolate chip cookie model, where the cookie itself is going to be our positive charge. And then we're going to have these negatively stuck electrons in the atom, and those would be the chocolate chips. So the cookie itself is positively charged, and we have these negatively charged chocolate chips smashed into the cookie. And he realized, and this is kind of the first time this happened, that Dalton's indestructible model, it wasn't really indestructible at all. It could be not destroyed necessarily, but broken down into further smaller pieces. And during his experiment, he found that with this Crookes tube, which turns out it was generating electrons, if these were passed through an electromagnetic field, they could be directed onto a screen to produce an image. And this is where we get, for example, electron microscopes, which can produce very fine, highly detailed images, and it has to do with using wavelengths of electrons versus visible light, which allow us to get that much finer detail. Now, the electrons in his experiment gave him this idea that there were both positive and negative forces working within the atom itself. So in his cathode ray tube experiment, he basically directed these cathode rays, or electrons, through this vacuum here, and we have this electromagnetic field being generated between these two plates. We have a magnet here that we can use to kind of direct that, and we could then move these electrons to a different part of our screen depending on the electromagnetic field being generated in this region here, and we could then produce an image on our screen. And since this was happening, since we were causing these charges, these cathode rays being moved throughout this electromagnetic field, it caused us to think that, well, those should be charged, or those could be charged. And when we see them kind of deflect and move towards the positive side of the field, well, Thomson had the idea that, well, maybe these cathode rays are negatively charged. And Thomson's model is going to look something like that, where we have a overall positive charge in the atom, and again these negatively stuck chocolate chips into the atom itself, dispersed throughout of it. Now, Ernest Rutherford was another major contributor to our atomic model, and again, not a whole lot of time had passed in between Rutherford and Thomson, and he came up with nucleus theory in the early 1900s, and his major contribution was the gold foil experiment. And this is probably one of the biggest things that you need to know from this lesson, is the results of the gold foil experiment and how it was set up. And he used alpha particles to do that experiment. And it's called nucleus theory because he was one of the first to really discover that an atom's mass is mostly centered in the nucleus. And it took the result of the gold foil experiment to realize this. He also realized within this experiment that the nucleus is what's going to have the positive charge. It's not necessarily the whole atom or evenly distributed, but it's concentrated in one area, and that would be in the nucleus. He also learned that electrons are going to be in fixed orbit. And because we have a nucleus and because we have electrons in an orbit around that nucleus, he came to the idea that the atom is going to be mostly empty space. And that's the biggest thing with this gold foil experiment. So what he did was he had this radioactive source, this alpha particle emitter, and he directed these alpha particles through a little slit and aimed them right at a thin piece of gold foil. And he thought, well, if Dalton was right, and an atom is a solid indestructible sphere, then the alpha particles should bounce off, and we should see those directed at the back part of our detector screen. But if Thomson was right, then the alpha particles should go right through the gold foil without breaking it. And it turns out that it was a mixture of both. So the results that he got showed that most of those alpha particles that were being shot through the gold foil went directly through. These are all the ones that we see right here. Those went straight through the gold foil without disrupting the gold foil, and we were able to detect them on the back side of the screen. There were a couple, however, that were deflected at angles that we'd get over on the side here. And we'll talk about the importance of those in a minute. As well as a couple that were deflected back. And these are the ones that we'd get towards the back side of the screen here. And what he got from this is that if most of these alpha particles are moving through the foil here, and they're going through undisrupted and not breaking the foil, then there must be mostly empty space in between those atoms. And because we had some that were deflected here, and alpha particles are positively charged, if we have deflection here, well, a positive and a positive are going to repel each other. So we see these couple that come off here because they're being repelled, and depending on the angle, we're seeing some that are being repelled straight backwards. And that's because of that positive-positive interaction. The positive alpha particle hitting the positively charged nucleus and interacting with it at short angles or at very sharp angles. Now the key with Rutherford's model is this open space that we have in between our electrons and our nucleus. And this is all open. We can see that these electrons are in an orbit around the nucleus. We're learning where charge is located specifically in the atom, and that's changed from previous models. And we're now realizing that they are separate. There are smaller particles that are or have different charges. And they're in motion in the atom, and they're not connected to each other. So the key here with Rutherford's model is that we realize that the atom, due to his gold foil experiment, is mostly empty space. Now Niels Bohr, again around the same time, early 1900s, comes up with the planetary model. And he basically said that the nucleus is going to be surrounded by orbiting electrons, at different energy levels. And this is the important part of the planetary model. He said that basically electrons are going to be in specific, energy-specific orbits. And this is where we get quantum energy theory from. He was one of the scientists that worked on the Manhattan Project, developing the first atomic bomb during World War II. And he said that these electrons at different energy levels can move back and forth between different energy levels depending on when they're heated or cooled. And when that happened, he realized that different elements gave off different colors of light when they were heated and cooled. And if we could direct that light through a prism, we can break up those lines or that color into different lines, which gives us this specific fingerprint for each element. And we'll learn about that in our next lesson. But the key here with the planetary model is the location, the specificity of where electrons are located. And they're now not only just in orbit around the nucleus, but in specific quantified energy levels. So Bohr's model said, okay, we have a higher energy level here, lower as we move, higher energy level as we move up in number. N equals 1 meaning lower energy, N equals 3 meaning higher energy. And as electrons move between these different energy levels, depending on how the electrons are moving, when they drop down to a lower energy level, they're giving off the extra energy that they had, and we're seeing these energy transitions being given off as photons or colors of light. So if we see an electron that in an element that gets excited by heating, let's say a sample of carbon, electrons in a carbon atom get excited, and their electrons jump from the first up to the third level. When that carbon atom cools down and this electron comes back down, it's going to eject a photon of light. And we're going to see that as a specific color of light. And this is going to be unique to every different element. Now with Bohr's model here, we see that in this atom of nitrogen, we have 2 electrons in our first level, and 1, 2, 3, 4, 5, total of 5 electrons in our second level. And these levels have different energies to them, and therefore cause the atom to have different properties. But again, the electron location here for our atom is becoming more specific. Now coming on to our most current model, Erwin Schrödinger and Werner Heisenberg, again in the 1900s, came up with the quantum along with several other scientists, Max Planck, Wolfgang Pauli, among others, also contributed to this quantum mechanical model, which was developed in 1926. And it said that electrons are in probability zones, which we call orbitals, not in orbits around the nucleus, and we can't pinpoint the exact location. With the speed that electrons move, the probability of actually pinpointing where it is was determined to be impossible. And since electrons are traveling in a wave-like motion as opposed to a particle-like motion, it made it even more difficult. So electrons exhibited both particle and wave behavior at the same time. And these quantum numbers were based on theories of Einstein and Planck. So basically this says that electrons are now located more specifically in specific energy orbitals, which will tell us that, for instance, this 1s orbital closest to the nucleus, this is going to be the highest probability of finding an electron. The 2s orbital, which moves a little bit further out to this region here, would be a less probability than the 1s, and as we move further out, either to the 3s or the 2p, it's changing the probability of how we might find an electron. And each of these orbitals is going to have a different quantified amount of energy. Now we can have principal energy levels like 1, 2, 3, 4, and then we can also have these sublevels like S, P, and D. For instance, the 1s orbital is going to be closest to our nucleus and our hydrogen atom, and then we can move further out. We can have sublevels P, D, and even further F, and we can move down our principal energy level. So in the second principal energy level, we can have a P, or 2p orbitals, excuse me, 3, and then we'd still have a 2s orbital as well. And these increase, you can see the different shapes here, as we move down the periodic table, and atoms get bigger, have more electrons, and therefore have more orbitals with changing probabilities of how we could find an electron. So what do you really need to know here? The important part with this is how the model changed throughout time. Specific location of subatomic particles, both protons and electrons, results of Thomson's cathode ray tube experiment, as well as Ernest Rutherford's gold foil experiment. The quantum model we also call the cloud model, as we represent the probability around a nucleus. This is probably not going to be the best drawing. And there's a good one on your notes at the end of your note packet that shows the cloud model with a density greater around the nucleus, indicating a higher probability of finding an electron there, and a less dense cloud towards the edge of the atom, indicating a smaller probability of finding a nucleus, or excuse me, of finding an electron. If you guys have any questions, make sure you write them down and come see me for any help. Have a great day.